Hey there, Gregory Carlson here. Welcome to the Calculus Building. So in the last video, we finally defeated Nero's stop sign once and for all, and we calculated our very first derivative. And so it's time to now define what a derivative is, or what it means for a function to be differentiable. Okay? So I'm going to say that, okay, a derivative exists at a point, and we'll call that point A. So a derivative exists at a point A if this limit exists. And you should be familiar with this limit. It's just the limit of the difference quotient that we've been working with. So a derivative exists at a point A if this limit exists at A. And it's as simple as that. If you have this derivative, this limit existing at a point, then that's what it means for that point to have a derivative. And there's an important connection between, and so by the way, we would say that the function is differentiable at that point. So there's an important connection between being differentiable and being continuous. So if a point is differentiable, meaning if that limit exists at that point, if it has a derivative there, then the point is automatically continuous. Do you remember when we talked about points being continuous? So if a point is differentiable, then the point is automatically continuous. So that's a little nice thing. However, and this is a big however, if a point is continuous, it is not necessarily differentiable. So that's really important. So if something is differentiable, that's kind of like the gold standard. If it's differentiable, you know it's automatically continuous. However, just because you're continuous doesn't mean you necessarily have a derivative there. You need this to exist in addition to being continuous in order to have a derivative. And so let's look at an example of when that happens. What is the derivative of the absolute value function at the point x equals 0? Well, hopefully you know what the absolute value function looks like. Looks kind of like this. V. And we see that something strange happens at the point of 0. We see that it has that corner, that sharp bend, that sharp corner right there. So what's going on right there? What is the instantaneous rate of change at that corner? Well, let's calculate it. And the way I'm going to calculate it is, what I'm going to do is I want to take the derivative of this function on the right half first and then the left half. Okay? So let's take the derivative when x is, assuming x is positive. So x is strictly greater than 0, and we're going to calculate this derivative. So, you know the definition. Let's find this limit as h approaches 0 of f of x plus h minus f of x all over h. So we're going to find that limit to find the derivative. So if x is bigger than 0, then we have, let's get our function, the limit as h approaches 0. Now, we have h on the bottom. F of x plus h, remember here's our function, so that's going to be the absolute value of x plus h minus the absolute value of x. Okay, so let's calculate what this is. Now, if x is strictly greater than 0, I'm going to just move this down here. If x is strictly greater than 0, then what's the absolute value of x plus h? Well, if x is positive, and by the way, we assume that h is positive when we're doing this limit. If h is positive as well, then we can just take off the absolute value signs and we won't get in trouble. Because both x and h are positive, so like 2 plus 5 is 7, absolute value of 7 is 7. So we won't get in trouble if We still have our limit here. We won't get in trouble if x is positive. We can just take off all of the absolute value signs. So good enough. X cancels with negative x, and so this is equal to the limit as h approaches 0 of h over h. Okay, sorry, I'm kind of into my graph here. Don't take the limit yet, because then we'd have 0 divided by 0, so that's no good. Instead, we can cancel these, h and h. So we get the limit as h approaches 0 of 1, which just equals 1. So if x is positive, if we're on this side of the absolute value equation, the derivative is 1. And that should make sense because right here, it's like we have the line y equals x. And as you know, that has a slope of up 1 over 1, up 1 over 1, up 1 over 1. So the derivative on this side of the graph is equal to 1. Okay? Now, let's calculate the derivative if x is less than 0. Okay, so we have the same thing as here. We have the absolute value of x plus h minus the absolute value of x over h, but this time x is less than 0. So this next part's a little bit tricky, but I'm going to try to explain it. X is negative and h is positive, but h is really, really small. Again, h is going to 0. So if x is negative and h is really small, what is the absolute value of x plus h equal to? Let me give you an example. Let's pretend that x is negative 5 and h is, say, 1. Okay? Then negative 5 plus 1 is equal to negative 4, and the absolute value of that would be 4. So if x was negative 5 and h was 1, this amount would equal 4, which is the same thing as x minus h. So if x is negative and h is really small but positive, it kind of takes away from the x. Don't you agree? So if x was negative 10 and h was 3, it takes away that 3 from the negative 10, so now it's negative 7. But then the absolute value makes it positive. So I know that's a little hard to understand, but if x is negative and h is positive and small, then the absolute value of x plus h would be the same thing as x minus h. Okay. Now, the absolute value of negative x, remember x is a negative number, that would still be a positive number. And we are dividing that by h. And so you can see that x cancels with negative x. And so we get the limit as h approaches 0 of negative h over h. Before we take that limit, let's cancel the h's. So we get the limit as h approaches 0 of negative 1. Now evaluate the limit, and you get negative 1. And so in other words, on this side of the function, the derivative is negative 1. And again, that should make sense to you because on this side of absolute value, we go down 1 over 1, down 1 over 1, down 1 over 1. So the slope is negative 1 everywhere. So we have the slope being negative 1, negative 1, negative 1, negative 1, negative 1. And then it instantly changes into 1, 1, 1, 1, 1. And so what is the slope at this point, at 0, 0? And the answer is this overall limit doesn't exist because you can't have these two things disagreeing with each other when you come at it from one side and come at it from the other side. This violent corner right here breaks the derivative at the point 0, 0 because our slope instantly teleports from negative 1 to 1. And that jump can't, the derivative limit can't handle that. So the derivative at 0 for the absolute value function does not exist. Now, it's important to point out that the absolute value function is continuous there. Because remember the definition of continuous, we have a point here, we have a limit coming from both ways that approach that point, and the point equals the limit of the graph. So we are continuous right there, but we don't have a derivative. And so this is an example of when we have a point that's continuous, but that actually doesn't have a derivative. Everywhere else there's a derivative, and by the way, that makes it continuous everywhere else. But at 0, it's continuous, but does not have this limit, so it's not a derivative. So when do derivatives not exist? Okay, I think that's a good question. If you have a corner, if you have a cusp, a derivative doesn't exist. And if you're not continuous, obviously a derivative can't exist. So if you have any of these, you have no derivative, or the derivative does not exist. So this question asks, on the following graph between 1 and 7, so between 1 and 7, but not including 1 and 7, okay, so just in between 1 and 7, where are we not differentiable? So it looks to me like this graph is smooth, 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 but right here we have a cusp. And if you try to calculate the derivative of a cusp, which is a graph that does kind of this thing, like a little sharp valley or something, you'll run into the same problem as a corner. So there's no derivative at 3. Here at 4, we see we're not continuous, so there's going to be no derivative at 4. And you can see we have a jump right here at 5, so we're not continuous at 5, so there's going to be no derivative at 5 either. So be on the lookout for corners, cusps, or any place the graph is not continuous and you know you're not going to have a derivative there. So I hope all of that made sense. We covered a lot of important ideas about differentiability. In the next section, we are going to be taking the derivative of more functions for practice. So I will see you there. If you like this video, please like and subscribe. Thank you so much.